Okay, so let us do now torque on an electric dipole. So we consider that this AB is an electric dipole. Obviously charges Q minus and Q plus placed in uniform electric field E. Now this positive charge will experience a force along the direction of field, which is F1 is equal to QE. But negative charge, magnitude wise same force, it will also feel QE, but direction will be opposite. So these two equal and opposite forces creates torque on this dipole kept in this uniform electric field. So if P is the dipole moment, E is the electric field making certain angle, then as per the cross product of vector, this tau will give the direction of the force, the torque on it. Now we know the torque is equal to magnitude of either force and distance between them. The magnitude is key, but what about the perpendicular distance between them? When we find perpendicular distance, it will be this BC. Angle is theta, so BC would be how much? 2a sine theta, right? So this is 2a sine theta, which means 2a sine theta. We have also done q into 2a will be the dipole moment. Therefore, tau becomes Pe sine theta. This is the formula we have for torque. Clear? So torque becomes Pe sine theta. Okay. Now, obviously, there is sine theta. So we may consider some case if theta it is 0 degree. We know the sine 0 is 0. Therefore, tau would be Pe sine 0 is equal to 0. So no torque will experience. This is also said to be the stable equilibrium, or there would be no movement in this. This is called stable equilibrium, right? Second case, if we take, so the second case, if we take theta 90, we know sine 90 is 1. So tau would be Pe sine 90 is equal to Pe. Or if you want, we can write in vector form also. So tau can be P cross E. And this is the unstable state, because this will be the maximum torque acting on it, unstable state. Hope it's clear. So similar to this, we have a topic which is called PE, potential energy of electric dipole, right? So when we talk about potential energy, this is all about the work required to do to change its orientation. What kind of work? Let's say, like in the previous diagram, if AB is in dipole, which makes, let's say, certain angle with the direction of applied field. So this is the dipole moment, keeping this as minus q and this as plus q. Let's say this makes, and if it makes angle theta 1, now if we change the orientation of this electric dipole and let's make it theta 2, so whatever work is done, that is stored in the form of its potential energy, work done to change its orientation or angle. So let's say for small change in angle, small work done dw, and over here tau into d theta. Tau we have already done, The formula for tau is what? It's P sine theta into d theta. So total work done, which is in the form of potential energy, symbol is U. So this PE is constant and sine theta d theta is integrated within the limit theta 1 to theta 2. So U becomes PE and sine integrated gives minus cos theta, and limit is theta 1 to theta 2. So U, let's write minus before PE, and this becomes cos theta 2 minus of cos theta 1. Therefore, we may write this U as minus. Minus can be converted into plus. If you want to write it to plus, then this cos theta 1 minus of cos theta 2. One form. And if you want to write in general, so then we can take theta 2 as 90. So cos 90 is how much? 0. Okay. Cos 90 is 0. And theta 1 as theta. Then U becomes, if write in the original, PE cos theta, right? And obviously it should be in minus P, because all forms of potential energy is negative, which means over here we can take theta 2 as theta. So theta 1 we can make 90, and thus minus P cos theta. So this is about the potential energy of n dipole. Thank you so much.